For more than 240 years, we have imagined objects whose gravity could trap even light. Today, we call them black holes. But the name has given almost everyone the wrong picture. A black hole is not an empty tunnel through space. It is not a cosmic drain. According to general relativity, it is a region of spacetime surrounded by a boundary that allows travel in only one direction. We have photographed their shadows. We have detected the waves produced when they collide. We can predict how stars orbit them and how gas behaves as it falls toward them. Yet the deeper we follow our own equations, the closer they lead us to a place where modern physics no longer has a complete answer. A black hole is not where our knowledge begins. It is where our best theories begin to reveal their limits. The first surprise is that physicists rarely think about black holes the way most people do. The word hole suggests an empty opening, a tunnel, a bottomless pit, something carved into space itself. But that is not what the theory of Einstein describes. A black hole is defined by the geometry of spacetime. More specifically, it is defined by a boundary called the event horizon. Nothing solid marks it. There is no physical surface, no invisible shell, no sudden collision waiting for anything that crosses it. If you were falling into a sufficiently large black hole, you might not notice the exact moment you passed the horizon at all. Local space could appear calm. Your clock would continue to tick, and for a brief time, nothing around you might seem unusual. That sounds impossible. How could you cross the most famous boundary in the universe without feeling anything? Because the event horizon is not a place where gravity suddenly becomes infinite, it is not a wall separating normal space from some strange substance. It is a causal boundary. It separates events that can still influence the outside universe from events that never can. Outside the horizon, light can still follow paths that lead away from the black hole. At the horizon, outward moving light can no longer increase its distance from it. Beyond the horizon, even light directed outward is carried toward a smaller radius. So why can nothing return to? Not because gravity is simply pulling harder than light can travel. Light always moves locally at the speed of light. The deeper reason is that space-time itself has been curved into a structure where every possible future leads farther inward. Outside a black hole, moving inward or outward is still a choice. Inside the horizon, that freedom disappears. Moving toward the center is no longer like choosing a direction through space. It becomes more like moving toward tomorrow. You can change how you reach the future, but you cannot choose a path that leads back into yesterday. Inside a black hole, the inward direction takes on that same inevitability. This is why the popular picture of a black hole as a giant vacuum cleaner is misleading. A black hole does not reach across the universe and drag everything toward it. From far away, its gravity behaves like the gravity of any other object with the same mass. If the sun were somehow replaced by a black hole with exactly the same mass, Earth would continue along essentially the same orbit. The solar system would become dark and cold, but the planets would not suddenly fall inward. What makes a black hole extraordinary is not that its gravity reaches farther than ordinary gravity. It is that enough mass has been compressed into a small enough region to create an event horizon. A black hole is not defined by what it pulls. It is defined by what can no longer escape. Once you understand that, another question immediately appears. If the event horizon is not a physical wall, how do we know black holes are really there? No one has ever looked inside one. According to classical general relativity, no signal from beyond the event horizon can return to the outside universe. No light, no radio wave, no message. Nothing carrying information about events after the crossing can come back. So black holes cannot be studied in the same way we study planets, stars, or clouds of gas. We do not see the interior. We see what the black hole does to everything around it. Astronomers watch stars orbit something massive and invisible at the center of the Milky Way. Their paths reveal millions of solar masses concentrated inside an extraordinarily small region. Elsewhere, gas spiraling toward compact objects is heated by friction and magnetic forces until it can outshine entire galaxies. That light comes from outside the event horizon, but it reveals the gravity shaping the material around it. Black holes also announce themselves through motion. When two of them orbit each other, they disturb spacetime. As the orbit shrinks, those disturbances travel outward as gravitational waves. In 2015, detectors on Earth measured one of these signals for the first time. The waves rose in frequency and amplitude as two black holes spiraled together and formed a final black hole that rang down toward a stable state. Then came another kind of evidence. The Event Horizon Telescope linked radio observatories across Earth to create a virtual telescope almost as large as the planet. It did not photograph the interior of a black hole. It could not. Instead, it imaged bright material surrounding a dark central region. That darkness was the shadow of the black hole, produced by extreme light bending and the capture of some light paths near the horizon. Different methods reveal different parts of the same picture. Stellar orbits reveal mass. Hot gas reveals the environment around the horizon. Gravitational waves reveal collisions. Black hole shadows reveal how light behaves in strongly curved spacetime. None of these observations gives us a direct view of the interior, but together they test the exterior predictions of general relativity from multiple directions. And those predictions have performed remarkably well. This is why black holes are no longer merely theoretical possibilities. They are physical objects with measurable masses, spins, environments, and collisions, which makes the next mystery even more surprising. If general relativity works so well, why do physicists still say that black holes are not fully understood? Because a theory can be extraordinarily successful without being complete. Every theory has a domain where it works. Beyond that domain, a deeper framework may be required. Newtonian gravity remains a powerful approximation for ordinary conditions. But Einstein revealed a deeper picture in which gravity is the curvature of spacetime, near extreme gravity. That difference becomes essential. General relativity predicted gravitational time dilation, gravitational waves, and black holes. Yet even a theory that extends an earlier one may eventually reveal limits of its own. When physicists follow the equations of Einstein into the interior of a black hole, the mathematics does not collapse at the event horizon. The horizon itself can be described smoothly. For a sufficiently large black hole, an observer falling through it may experience no dramatic local event at the crossing. The equations continue inward. The trouble appears deeper inside. As matter collapses and curvature grows, general relativity predicts that the interior evolves toward a singularity. The word is often used as though it describes a confirmed object, a point of infinite density. But that picture is more certain than the physics allows. A singularity is a feature of the mathematical description. It indicates that quantities such as curvature become unbounded, and that the classical theory can no longer extend space-time in the usual way. That does not automatically mean nature contains a physical point with literal infinity packed inside it. In physics, infinity often functions as a warning. It may signal that a theory has been pushed beyond the conditions where it can provide a complete description. Older theories have produced infinite answers that disappeared when deeper frameworks were developed. The infinity was not the final object. It was evidence that something was missing. The singularity inside a black hole may play the same role. It may not tell us what matter ultimately becomes. It may tell us that general relativity has reached the edge of its domain. The equations continue, but our confidence in the physical picture does not. So what theory should take over? The obvious place to look is quantum physics. Quantum theory describes matter at microscopic scales. General relativity describes gravity and the geometry of spacetime. In most situations, the two frameworks can be used separately. Deep inside a black hole, that separation can no longer hold. Gravity becomes extreme. Matter is driven toward incredibly small scales, and both theories must contribute to the same physical description. Yet general relativity treats spacetime as smooth, while quantum physics describes a world of quantum states, fluctuations, and uncertainty. Under extreme conditions, those descriptions no longer fit together cleanly. Physicists have proposed many possible solutions. Some approaches suggest that spacetime has a quantum structure rather than being perfectly smooth. Others propose that spacetime itself emerges from deeper quantum relationships. These ideas may remove the classical singularity, reproduce important features of black hole thermodynamics, or radically change our picture of the interior. But none has been confirmed as the complete theory of quantum gravity. The main difficulty is experimental. Quantum gravity should become unmistakable only at extraordinarily small scales, often in regions hidden behind event horizons or under conditions we cannot reproduce. We can test black holes from the outside, but directly probing the quantum structure of their interiors remains beyond our present reach. The available evidence has not yet selected one complete theory. That alone would make black holes central to modern physics. But the problem does not remain hidden inside. Quantum theory creates another conflict that can be described entirely from the outside. A conflict involving information. Imagine throwing a book into a black hole. The book is not important because of its story. What matters is its physical state, the arrangement of ink, the structure of the paper, the positions of atoms, the quantum information describing the matter from which it is made. Once the book crosses the event horizon, no classical signal can return. From the outside, the information becomes inaccessible. For a long time, that seems strange, but not necessarily contradictory. The information could still exist inside the black hole. We simply could not reach it. Then Stephen Hawking applied quantum field theory to the region around the event horizon. The result changed black hole physics. Black holes should not be completely black. They should emit radiation. The effect is not caused by ordinary matter escaping from inside. It arises from the behavior of quantum fields in curved spacetime near the horizon. To a distant observer, the black hole behaves as though it has a temperature. It slowly radiates energy. As it loses energy, it loses mass. Over an immense period of time, it shrinks. For a black hole formed from a star, the process would be unimaginably slow. Its lifetime would exceed the current age of the universe by an enormous amount. But the theoretical endpoint matters. If Hawking radiation continues, the black hole can eventually evaporate. The black hole and its horizon are gone. From the outside, only the radiation remains. So where is the information? In ordinary quantum mechanics, information is preserved. A physical system may become complicated. its state may become scrambled so thoroughly that no practical observer could reconstruct the past. But the underlying evolution is not supposed to erase information from reality. The original calculation by Hawking appeared to create a serious problem. The radiation looked thermal. It appeared to depend only on a few broad properties of the black hole. It did not seem to contain the detailed information describing everything that had fallen in. If the black hole vanished and only featureless thermal radiation remained, different initial states could produce the same final state. The information would be fundamentally destroyed. That would violate a central principle of quantum theory. This conflict became known as the black hole information paradox. It is not merely a puzzle about whether a book can be recovered. It is a conflict between the structure of quantum mechanics and the behavior of spacetime. If information is destroyed, quantum theory may require revision. If information is preserved in the radiation, physics must explain how that encoding occurs without allowing ordinary signals to escape from behind the horizon. For decades, this problem has driven research across gravity, quantum theory, thermodynamics, and information science. Many physicists now expect that information is preserved. Modern calculations suggest that Hawking radiation may contain subtle correlations capable of encoding it. Black hole entropy also scales with the area of the horizon, rather than the volume of the interior. That relationship suggests that spacetime and information may be connected more deeply than classical physics allows. But a successful calculation is not yet the same as a complete physical picture. We still do not have an experimentally verified description of the entire process. We do not know exactly how infalling information becomes encoded in outgoing radiation. We do not know whether the horizon remains smooth throughout evaporation, or whether the classical interior survives at all. Some proposals preserve a smooth horizon. Others predict violent quantum effects, or suggest that the interior is encoded in the exterior description. The disagreement does not mean physics has made no progress. It means the problem has become more precise. A complete theory must explain how information, causality, and the geometry of spacetime fit together under the most extreme conditions. This is why black holes are more than astronomical objects. They are laboratories where physicists test whether spacetime is fundamental, whether geometry can emerge from quantum information, and whether gravity and quantum physics belong to one deeper framework. Black holes are not symbols of complete ignorance. From the outside, they are among the great successes of modern physics. Follow general relativity deep enough, and it points toward a singularity where the classical description appears incomplete. Add quantum fields, and the black hole begins to radiate. Allow it to evaporate, and the fate of information becomes impossible to ignore. At every stage, black holes push successful theories into regimes where their hidden assumptions become visible. That does not mean Einstein was wrong. It means general relativity may be part of a larger structure. Newtonian gravity was not erased by Einstein. It survived as an approximation that works under ordinary conditions. A future theory of quantum gravity may preserve everything Einstein explained, while revealing what replaces the singularity and how information survives black hole evaporation. We do not yet know, and that uncertainty is not a weakness in the story. It is the story. For more than 240 years, physicists have tried to understand objects capable of trapping light. The explanation has changed from Newtonian dark stars to relativistic event horizons. The evidence has changed from speculation to stellar orbits, gravitational waves, and black hole shadows. Our models have become more precise. Our measurements have become more powerful. And the mystery has moved. It is no longer whether black holes exist. It is no longer whether general relativity can describe their exterior. The deeper question is what happens when gravity, spacetime, and quantum information can no longer be separated. So perhaps the greatest misconception about black holes was never that they swallow light. It was that they were simply holes. In reality, they mark the boundary between what modern physics can describe with extraordinary precision and what it still cannot fully explain. They are places where geometry determines the future, where a boundary exists without a wall, where one of our greatest theories succeeds so completely that it reveals the exact point where success is no longer enough. Black holes do not merely hide matter from the universe. They expose the limits of the ideas we use to describe the universe, and until gravity and quantum physics can speak the same language, black holes will remain more than objects in the darkness. They will remain the frontier of our understanding of reality itself.